So, good morning, students. Today we are going to discuss about low temperature physics chapter, that is unit 2 in our thermal physics course. Okay. So, in this one today we are going to discuss about what is Joule-Thomson effect and porous plug experiment and its results, and we will obtain an expression for the cooling produced when the gas suffers Joule-Thomson effect. So, here first of all, let us discuss what is Joule-Thomson effect. So, see, when a gas under high pressure is passed through a porous plug, it cools, which is known as Joule Kelvin or Joule-Thomson effect. Okay. So, I will explain a little bit. Just see here. చూడండి, మనకు ఆల్రెడీ ఇంతకుముందు మేము క్లాసులో చెప్పుకున్నాం. ఆల్రెడీ ఏమంటే ఒక మనం ఇళ్లలో ఆస్బెస్టాస్ పైప్ కొని ఉంటుంది కదా, నార్మల్ గా లేటెస్ట్ పీవీసీ పైప్ తీసుకున్నాం. ఈ పీవీసీ పైప్ తీసుకున్నాం. ఆ పీవీసీ పైప్ లో ఏం చేసినామంటే మనకి కాటన్ ఉంటుంది కదా, మన ఇళ్ళ దగ్గర కాటన్ ఉంటుంది కదా, వూల్ కాటన్ ఉంటుంది కదా. కాటన్ ఏం చేసినామంటే ఇట్లా పెట్టినాం. పెట్టిన తర్వాత ఏం చేసినామంటే ఇటువైపు ఒక పిస్టన్ ఉంది, ఇటువైపు ఒక పిస్టన్ ఉంది, ఇటువైపు ఒక పిస్టన్ ఉంది అనుకోండి. ఫర్ ఎగ్జాంపుల్ ఎట్లా పిస్టన్స్ ఉన్నాయి, పిస్టన్స్ ఉన్నాయి ఇట్లా. ఇటువైపు ఒక పిస్టన్ ఉంది. పిస్టన్ అంటే మీకు ఆల్రెడీ చాలా సార్లు చెప్పిన. ఇటువైపు ఒక పిస్టన్ ఉంది, ఇటువైపు ఒక పిస్టన్ ఉంది అనుకోండి. ఫర్ ఎగ్జాంపుల్ ఈ రెండింటిని బాగా ఒత్తితే ఏమవుతుందంటే ఇది బాగా నేరోగా తయారవుతుంది ఇట్లా. సో దీన్ని ఏమంటామంటే మనం పోరస్ ప్లగ్ అంటాం. అంటే ఇట్లా రెండు వైపులా ఇట్లా ప్రెస్ చేస్తే, అంటే ఈ పిస్టన్ యూజ్ చేసుకుని రెండు వైపులా ప్రెస్ చేస్తే ఒక బాగా అంటే అటువైపు నుంచి ఇటువైపు గ్యాస్ ఈజీగా వెళ్ళలేని ఒక లేయర్ ఏర్పడుతుంది, కాటన్ లేయర్. దాన్ని మనం ఏమంటామంటున్నామంటే వీఆర్ కాలింగ్ ఇట్ యాస్ పోరస్ ప్లగ్ అంటున్నాం, పోరస్ ప్లగ్. ఓకే. సో ఈ ఎక్స్పెరిమెంట్ ఏం చేస్తామంటే ఈ పోరస్ ప్లగ్ తయారు చేసినాం ఆల్రెడీ. సో వాట్ వీ హ్యావ్ ఎ పైప్ that is same PVC pipe kind of thing. So we have a porous plug like this. So we have a porous plug like this. So that means our wool or cotton is there. So we have this kind of structure. Let us consider this is the first side, this is the first side, this is the second side of porous plug. Okay. So this side the pressure is P1, volume is V1, and temperature of the gas. So all these are pressure P1 is the pressure of the gas, which is this, on this side. So this is side 1. Let us say this is side 2. Okay. So V1 is the volume of the gas this side, and T1 is the temperature of the gas this side. So coming to this side, here the pressure is P2 and volume is V2 and temperature 2 of the gas this side. So suppose let us consider gas pressure is more this side, let us say. So what we are doing, we have a piston like this, this kind of arrangement. So by using this piston, we have pushed this piston, So after pressing the piston, the pressure P1 will be more. Okay. What happens, because this side pressure is more, pressure P1 is more when compared to P2. That's why the gas enters this side. Very slowly gas enters this side. So in this process, what happens, if the temperature of the gas in this side is T1, after passing through this porous plug, the temperature will decrease. That means T1 will be greater than T2. That means there is a temperature fall. How much fall? When we start initially, let us say for the just for comparison, let us assume that. So this is our porous plug. Okay. This is our porous plug. This is the arrangement. Let us say this is a piston. Okay. So for the timing, what we are considering is these are P1, V1, V2, T1. This is P2, V2 and T2. Okay. So for the timing, that is at t is equal to 0 time, let us say when we are starting, let us consider P1 is equal to P2 V1 is equal to V2 and T1 is equal to T2 for the time being. Okay. So after some time, what we have done, we have pushed this piston. We have pushed this piston in this direction. So what happens? The pressure P1 will be increasing. Okay. Obviously V1 will be decreasing because we are pushing, right? So the volume will be decreasing, pressure will be increasing, and the temperature also increases. So what happens? The gas, because of from high pressure to low, always gas goes from high pressure region to low pressure region. So gas, it goes like this. In this process, what happens? Initial temperature of this gas, this side is, let us say, T2. So the gas suffers a cooling. The temperature will be reduced. Let us call TF is the final pressure after this process. This side, TF will be always less than T2. That means temperature falls in the gas. So this is called porous plug experiment. Okay. So now let us come to this topic. So if we consider, when a gas under high pressure is passed through a porous plug, it cools, which is known as Joule Kelvin or Joule Thomson effect. Okay. So this Joule Kelvin or Joule Thomson, what they have done, they have conducted an experiment. Based on that experiment, they have derived some results, and they wrote an equation also. How much, suppose the gas is going from high pressure region to low pressure region, how much fall will temperature, how much temperature fall will be there? They have calculated mathematically, and we will derive that equation also. Okay. So just consider this figure. Just watch this figure. In this figure, what is there? Here, this is our porous plug. This one, this total is porous plug. Okay. So what happens here? Here a pump is there, a piston is there. Here, just observe. This is a piston. That arrangement is they have done a machining, and they have arrived this kind of machine. This we are going to use for porous plug experiment. Okay, just observe this figure. So this side, this is our first side. This is our first side. This is our second side. Okay. So this side pressure is P2, volume is V2, and temperature is T2. This side pressure is P1, temperature is volume is V1, and temperature is T1. Just you observe this figure. In this figure, what is there? Very big kind of beaker kind of big, very big. It will be of the order size of what our bucket or water drum. Okay. Let us say this kind of this is made up of glass. Okay. In that glass, water is there. This is water. Water is there. In that water, one arrangement will be there. In that arrangement, this porous plug is fixed with a beaker. In that beaker, we keep ice for cooling purpose. Ice for cooling purpose. This is ice. This is our porous plug. This small one is porous plug. That porous plug is there in this structure. That is our asbestos. Okay. So this is porous plug. So this one, this total part is our porous plug now. Okay. Just remember. So this kind of arrangement is there. But here, this is piston. This is piston. This one is piston. So initially, both the sides, let us consider both the sides, temperatures and pressures and volumes, everything same. Let us say here, let us say it is closed structure. So initially, both the sides, temperature, pressure, and volume, everything will be same. So what we are doing is we are just pushing this piston like this. We are pushing the piston. Because we are pushing the piston, we are compressing this gas. So this side, obviously pressure increases. So pressure increases and volume decreases. Okay. Here volume is fixed. Okay, no problem. So temperature increases. That we are going to measure with the help of this thermocouple. This is thermocouple. This one and this one are thermocouples. So thermocouple, what they do, they measure the temperatures. They measure the temperature. Okay. So these thermocouples are measuring the temperature. So this thermocouple is measuring the temperature this side. This thermocouple is measuring the temperature the other side. Okay. So when we are pushing this piston, the pressure of the gas increases this side. So that means the temperature of the gas increases. But here we have water here. So water here and the ice here. So both side temperatures will be again same. But here the gas is at high pressure. So what it does, it goes on passing this side. It passes that side. When it passing that side, the temperature this side falls below T2. So like this, many cycles will happen. So in this process, we'll get temperatures below 62 Kelvin like that. So after doing many cycles like this. So this is the process of our Joule Kelvin experiment. So let me come to this one. So the apparatus consists of a cylindrical tube made up of non-conducting material. So this is cylindrical tube. It is made up of non-conducting material. At its center, there are two metal discs. Its center, here metal discs are there. This one is metal disc. This one is metal disc, which are perforated. The space between them is stuffed with a porous material like silk or cotton wool. This is porous plug. Okay. So this side metal piece is there. This side also metal piece there. By using those metal pieces, we have pressed that cotton. So this forms the porous plug. The tube is surrounded by a jacket packed with a pellet or asbestos, so that heat from inside may not be transmitted to the outside, vice versa. So this is asbestos. Because asbestos is a very bad conductor. It doesn't conduct heat outside or inside. So that's why when we are pushing this porous plug, the air temperature increases. That won't be conducted outside. Okay. So this cylindrical this is further surrounded by a outer cylinder containing water, so that heat may not be conducted from outside to inside the tube. So there are two sensitive platinum resistant thermometers. So there is two thermometers will be there. This one and the other side one. These are thermocouples. We use them as thermometers to measure the temperature. Okay. So now let us come to the working. A gas is compressed under high pressure, and the heat of compression is removed by the passing through the coil surrounded by freezing the mixture. The cooled gas under high pressure and under low pressure is allowed to pass through the porous plug. The gas suffers Joule Kelvin expansion while passing through the porous plug. The temperature of the gas at inlet and outlet are measured. So Joule Kelvin conducted a number of experiments with the different gases under different conditions. They arrived at the following conclusions. So they have what they have done. They have taken different gases. Suppose for the time at one time they have taken, let us say, oxygen gas. Next time they have taken neon gas. Next time they have taken nitrogen gas. Like this, they have studied Joule and Kelvin. They have studied in a number of cases. And after studying this Joule Kelvin porous plug effect, Joule Kelvin effect for many gases, they have arrived at these points, these conclusions. So these are the conclusions. I will read out once. We have already discussed. Just read out once. Just see. All gases except a few suffered cooling after passing through the plug. So this is our porous plug. Okay, this is our porous plug. So all gases are, when they are going from high pressure region to low pressure region, they are suffering temperature fall. That means this side, when gas is passing from this side, let us say temperature is, this side is T1. After passing this gas to this side, when this is high pressure region, this is low pressure region, the gas temperature is decreasing. That means T2 is less than T1. So, but there is an exception case, like all gases except a few, that few will discuss later, suffered cooling after passing through the porous plug. Okay. At ordinary temperature, while most of the gases showed cooling, hydrogen and helium suffered heating effect after passing through the plug. Here, just remember, actually, there is a temperature called inversion temperature. Inversion temperature. Inversion temperature, we denote it by Ti. Okay. So, in generally, the equation of state of a gas is given by van der Waals equation. That is P plus A by V square into V minus B is equal to RT. This is van der Waals gas equation. This applies for all gases. That can be either ideal gas or real gas. Okay. It applies for all the gases. Okay. So this is a constant and this is also constant. So this temperature of inversion comes like 2A by RB. This is an equation we will derive later. So here A is a constant of this, A and B are van der Waals constants, and R is the universal gas constant. Okay. So here we have to remember one thing. This is temperature of inversion. That means the gas, it passes through from higher pressure to lower pressure. Let us say this side temperature T1, this side temperature T2. Okay. So it is going gas from higher pressure to low pressure. But if the temperature initially, this is initial temperature T1, let us say T1, if it is less than Ti, temperature of inversion, the gas doesn't suffer any cooling. So this is called temperature of inversion. So if the gas temperature, that is T1, greater than Ti, the gas suffers cooling. So this is very important characteristics of the gas. What we are going to consider. So for hydrogen and helium, I already told you that we can attain maximum cooling up to 62 Kelvin only by using this Joule Kelvin Porous plug experiment. Okay, but for temperature of inversion will be less than this 62 Kelvin for hydrogen and helium. That's why they are heating. They are showing heating effect. Okay. So next point, the higher the pressure difference of the gas between the two sides of the plug, the greater is the cooling of the same initial temperature. That means this is proportional. Suppose pressure difference is first side is pressure P1, second side pressure is P2. This temperature fall, let us call it as d tau, dt, temperature fall. dt means T1 minus T2 is dt, let us call. This dt will be proportional to the pressure difference on both the sides. Next one, the lower the initial temperature, greater is the fall of the temperature. But this doesn't apply for helium and hydrogen. Just remember. Okay. The lower is the initial temperature, the greater is the fall of the temperature on passing through the plug. So for the same difference of pressure between the two sides of the tube. Suppose this is the pressure P1 this side, this is the pressure P2 other side. So this is a porous plug. This is a pressure this side. This is a pressure P2 this side. Okay. So let us say we'll keep 25 degrees here, and we have done this experiment. Let us see the fall in the temperature is dt1. Okay. Next, same thing we have taken same porous plug. The pressure is P1 same, and this side also pressure is P2 same. But the temperature is now, let us say 23 degrees. So when the gas goes from this side to this side, the temperature fall let us call as dt2. So from this, according to this point, what happens? dt2 is less than dt1. That means when the initial temperature of the gas is less, then the cooling will be more. That is this point. So the lower the initial temperature, the greater is the fall of the temperature on passing through the plug for the same difference of pressure between the two sides of the tube. So this is the explanation. Next, coming to 5th point, the initial temperature of the gas increases when the pressure difference between the two sides of the plug is constant. The cooling decreases, and at one particular temperature, the gas neither suffers in cooling nor heating. Such temperature is called as inversion temperature or temperature of inversion. This I have already explained. So as the initial temperature of the gas increases, that means this temperature increases when we are going on increasing this temperature. At one particular pressure, at one particular temperature, the gas neither suffers cooling nor heating. That particular temperature is called as temperature of inversion. So for the time being, we'll keep it here. We'll discuss the temperature of inversion later. So these are the conclusions they have arrived by studying number of gases, the effect of Joule Kelvin effect on number of gases. Okay. So now let us derive an expression for Joule-Thomson cooling. Okay. So this one I have already explained. So this is a porous plug. This is asbestos. Just we have taken a portion of one minute. This is asbestos. Asbestos means it's a pipe made up of ceramic material. Okay, it's a pipe made up of ceramic material. This that is ceramic material is asbestos. Okay, so in this one, this two pistons have. This is porous plug. Porous plug have been inserted. This side one metal piece will be there. This side also a metal piece will be there. So this porous plug is fitted with, let us say, two pistons. One is piston A, the other one is piston B. So this is a porous plug. So this side pressure is P1, volume is V1, and let us assume the temperature also T1. This side is pressure P2, volume is V2, the temperature is T2. Okay, initially. So now let us derive an expression.
Hello, sir.
చెప్పమ్మా.
ఏమైంది సార్ స్ట్రక్ ఆపిరు?
ఒక నిమిషం ఆగమ్మా.
ఓకే సార్.
చూడండమ్మా. So consider this is a cylinder. Consider a thermally insulated cylinder. PQ. This cylinder is PQ. This is P. This is Q. This is a cylinder made up of asbestos. Just remember, divided into two portions by a porous plug. This is porous plug Z, and fitted with the two non-conducting pistons A and B. These are non-conducting pistons. These valves are made up of insulating material. The walls of the pistons. This is a piston. This is also piston. These walls are made up of non-conducting material. That means insulator, non-conducting materials. Okay. So this is a porous plug. That is G, and this PQ is this one cylinder, which is divided into two portions by the porous plug. This side is pressure P1. This side is pressure P2. Suppose the piston A pours slowly 1 gram mole of the gas through the porous plug at constant pressure P1. So what we are doing now? So this is a porous plug. Now we are pushing this piston. To make the pressure P1 increases a little bit. Okay. So now the escaping gas, that means the gas will be, this is porous plug now. This is pressure, this is higher this side. So that's why what happens, the gas tries to escape from this side to this side. So pushes back the position piston B, here piston A, this is piston A, this is piston B. So what happens, the gas comes from this side to this side. So the piston B at a smaller constant pressure P2, let V1 and V2 be the volumes of the gas before and after passing through the porous plug respectively. So this V1 is when we do the volumes of the gas before and after passing through the porous plug respectively. And what we have done, we have pushed this piston. Because of that, what happens, the gas is trying to escape from this side to this side. In that process, some work will be done. So external work done on the gas by the piston is P1 into V1. Because I already told so many times, the work is given by W is equal to P into V. Just remember this equation. Okay. So we are pushing the piston. We are pushing the piston A. In that process, what we are doing some external work on the gas. In this side gas is there, right? We are doing the work on the gas by the piston A. That is P1 into V1, because this side is pressure is P1, volume is V1. This side pressure is P2, and the volume is V2. Okay. So the external work done by the gas on the piston. Here, what we are doing, we are pushing the piston this side. That means we are doing work on the gas up this side. So after what it does, so because the pressure is this side is more, that's why the gas escapes this side. So what this gas, what it does, it moves the piston. This piston, it pushes the piston. In that process, this piston will be replaced because it is here. Now it may be moved here. This is a new position of the piston. Okay. So the external work done by the gas on the piston P2 B, on the piston B. This is the piston A. Okay. So this is P2 V2. So net amount of work, external work done by the gas. So how much net work done by the gas? So how much work is the gas is doing? That means the work done by the gas minus the work done by the piston A. That means we have to remove, we have to minus this one from this one. That means P2 minus P2, P2 V2 minus P1 V1. Okay. So in addition to this, what is happening? The gas performs internal work also to pull its molecules further apart against their mutual interaction forces while passing through the porous plug. So just remember this one. In addition to this, the gas performs internal work also to pull its molecules further apart against their mutual attraction forces while passing through the porous plug. I will explain, just see. So what happened? Actually, initially this side the gas is there. This porous plug. Initially gas is this one piston. This other piston. This is piston B. This is piston A. So when we push this piston, the gas molecules will be just this piston. What happened? The piston came here. This is piston A. Came here. Let us call this position is X. This position Y. The piston came from position A to X to Y. Because of that, the volume decreases. That means gas molecules come together. That means move a little bit closer because the volume is decreased. Number of molecules is the same, but because we have pushed this piston, the gas distance between the gas molecules is decreased. But when it is going from this side to this side, this piston expanding. That means the pressure P2 is same. So that means the gas expands this side. The gas expands this side. In that process, it do some external work. That means internal work also. It increases the distance between the molecules. Okay, because this side volume is more. So the internal work done when the 1 gram mole of the gas expands from volume V1 to V2, because this side is volume V1, this side is V2. So gas is expanding. So in that process, how much work will be done? That we have to calculate. So this is the work. How we will calculate this work? Just observe. I will tell you the equation. So just remember this equation. This equation. Okay. So we know already that the work done on a gas, work done by the gas is equal to integral P dV. Okay. So in this one, the internal work done by the gas is given by this term. The internal work done by the gas will be given by this term. Okay. This is the external work. P into V is the external work. P into V is the external work. Internal work done by the system is given by this term. So instead of P, the internal work we are calculating here. So instead of P, we will substitute A by V square. A by V square into dV. So if we calculate, we will get this one. A is some constant, that is water wall constant. A by V1 minus A by V2, because initial pressure is V1. Initial volume is V1, final volume is V2. So the total work done by the gas, because the gas is doing work in two types. One is in moving the piston B to by doing some work, and it is also doing internal work. So we have to add both of them. So the total work done by the gas is W is equal to P2 minus P1, the above equation plus this one. So this is the total work done by the gas. Just remember this equation. This is the total work done by the gas. This is the total work done by the gas. Next, I have already explained this water wall equation, but according to water wall equation, P plus A by V is 2 V square. This is not V2. P plus A by V square into V minus B is equal to RT. This is water wall equation. Okay, this is not 2. This is V square. Okay, this is water wall equation. If you expand this equation, PV plus A by V minus PB is equal to minus A by AB by V square is equal to RT comes. But these are the small constants. A and B are small constants. Because volume is very, very high, so this will be also very, very high. So we can neglect this term. So after neglecting this term, we can write this water wall equation like this: PV plus A by V minus PB is equal to RT. So we'll keep PV only this time. PowerPoint. Hello.